100 tons of iron and steel, climbing a grade that would stall any conventional locomotive, pulling a train of loaded log cars up slopes that seem impossible, following tracks so rough and temporary that mainline railroads would condemn it as unusable, navigating curves so tight that the entire train bent like a snake. This wasn't experimental. This wasn't a one-off engineering stunt. This was standard operation for thousands of locomotives built specifically for logging railroads between 1880 and 1945. They were called shays, named after Ephraim Shay, a logger from Michigan who looked at the problem of getting timber out of mountainous terrain and designed a locomotive that broke every assumption of conventional railroad engineering. Standard locomotives, the kind that pulled passenger trains and freight across the continent, were direct drive machines. The steam cylinders drove rods connected directly to the driving wheels. They were fast, powerful on level ground, and completely useless on the steep, winding, poorly constructed track that logging railroads required. They would slip, stall, or derail. Shay's innovation was deceptively simple. Instead of direct drive, he used a geared drive. The cylinders drove a shaft running along the side of the locomotive, and that shaft drove all the wheels through bevel gears. It was slow, 10 miles an hour maximum, but it could climb grades of 8, 9, 10% while pulling loads that weighed more than the locomotive itself. And it could do this on track that was little more than rails spiked to ties laid on cleared ground. Between 1880 and 1945, approximately 2,700 Shay locomotives were built, most of them by the Lima Locomotive Works in Ohio. They worked in the forests of the Pacific Northwest, the Appalachians, the Sierra Nevada, hauling billions of board feet of timber from places that had been inaccessible before. And then, as quickly as they had appeared, they were made obsolete by trucks and diesel power, and the logging railroads were abandoned, the track pulled up, the locomotives scrapped or left to rust in the woods. Today, maybe 160 Shays survive, scattered in museums and on heritage railroads. A handful are still operational, pulling tourists on the same grades they once climbed with loads of timber. This is the story of the Shay locomotive, the machine that climbed mountains, the invention of a logger who became an engineer, and the transformation of an industry. Let's start with the problem, because the Shay was designed to solve a specific, urgent challenge that conventional technology couldn't address. By the late 1800s, the accessible timber in the eastern United States was largely gone, cut and milled. The industry was moving west into the Appalachians, the upper Midwest, and the Pacific forests. But these forests weren't conveniently located near rivers or on flat ground. They were in mountains, on steep slopes, in terrain that made traditional logging methods difficult or impossible. The old system, cutting in winter, skidding logs to riverbanks, and floating them downstream in the spring drive, had limitations. It was seasonal, dependent on ice and snowmelt. It was geographically restricted to areas with navigable rivers. And it was risky, prone to log jams and loss of timber. Animal power. Horse teams and ox teams pulling logs on sleds or high wheels was limited by terrain and capacity. A team could move logs a few miles over relatively flat ground, but in steep mountains, with ravines and creeks and slopes too steep for animals, it didn't work. The industry needed year-round transport, high capacity, and the ability to reach timber in terrain that animals couldn't handle. Railroads were the obvious solution. Rails could operate in any weather, could move massive tonnages, and could be built almost anywhere. But standard railroads required gentle grades, typically no more than 2 to 3% for freight operations, and wide, sweeping curves. Building a standard railroad into mountainous logging country meant extensive grading, cuts and fills, tunnels, and heavy trestles, all of which were prohibitively expensive for temporary logging operations. Standard locomotives compounded the problem. A conventional locomotive, the kind used on mainline railroads, had a rigid frame. The driving wheels, the large wheels that were powered, were fixed in position. The locomotive's weight rested on these driving wheels, and traction came from the weight and the friction between the wheel and the rail. This worked well on level or gently graded track with smooth curves. But on steep grades, the weight distribution shifted, reducing the weight on the driving wheels and reducing traction. At 3 or 4% grades, a standard locomotive would slip, the wheels spinning uselessly. And on tight curves, the rigid wheelbase meant the locomotive couldn't conform to the track. The wheels would try to go straight, the rail would force them to turn, and the result was derailment or excessive wear on wheels and rails. Logging operations needed to climb grades of 6, 8, 10% or more. They needed to navigate curves of 20, 30 degrees, curves so tight that the train bent visibly. And they needed to do this on track that was temporary, cheaply built, often little more than rails spiked to ties laid directly on the ground. Standard locomotives couldn't do it. The industry needed something different. Ephraim Shea was a logger, not a trained engineer. Born in 1839 in Ohio, he worked in the timber industry in Michigan, operating sawmills and logging camps. In the 1870s, Shea was logging in the hills near Cadillac, Michigan, and he faced the same problem as everyone else in the business. Logs cut on steep slopes, miles from the mill, with no practical way to get them out. Shea had a mechanical aptitude, the kind of hands-on, problem-solving ability that comes from building and repairing equipment in remote locations with limited resources. He looked at the problem and thought about locomotives. He understood that standard locomotives couldn't handle steep grades or tight curves because of their rigid design and their reliance on a few driving wheels for traction. His insight was to change both. Instead of a rigid frame, use a flexible frame. Instead of driving a few wheels, drive all of them. And instead of direct drive, which required the wheels to turn at the speed determined by the cylinder stroke, use gears to reduce speed and multiply torque. Shea built his first prototype sometime between 1877 and 1880. The exact date is unclear, and the machine itself doesn't survive, but accounts describe it as a small locomotive with vertical cylinders mounted on one side, driving a shaft that ran along the length of the locomotive. The shaft had bevel gears that engaged gears on each axle, driving all the wheels. The entire locomotive was mounted on 2 four-wheel trucks that could pivot independently, allowing the locomotive to follow curves and uneven track. Shea tested the machine on his own logging railroad, and it worked. It climbed grades that would have stopped a standard locomotive. It navigated curves that would have derailed one. And it operated reliably on rough, temporary track. Word spread. Other logging operators heard about Shea's machine and wanted one. Shea didn't have the resources to manufacture locomotives at scale, so he licensed the design to the Lima Machine Works in Lima, Ohio, later renamed the Lima Locomotive Works. Lima began producing Sheas commercially in the early 1880s, and the design was refined and standardized over the next few years. Shea patented the design in 1881, U.S. patent number 249-364, covering the key elements: the geared drive, the vertical cylinders, and the articulated frame. The patent gave Shea and Lima a monopoly on the design, and Lima became the dominant manufacturer of geared locomotives. Shea himself continued logging, used his royalties to expand his operations, but never became wealthy from the invention. He faced patent disputes, competition from other geared designs, and the usual challenges of the timber industry. He died in 1916, known in the industry but not famous outside it. The locomotive that bore his name, however, became ubiquitous. To understand why the Shea worked where standard locomotives failed, you have to understand the engineering. A standard locomotive has horizontal cylinders mounted inside or outside the frame. The pistons drive rods that connect to the driving wheels, typically the large center wheels. When steam enters the cylinder, the piston moves, the rod pushes, and the wheel turns. The wheel is directly connected to the rail, and the locomotive moves forward. This is efficient and simple, but it has limitations. The speed of the locomotive is directly tied to the piston stroke and the wheel diameter. To go faster, You either increase the piston speed, which has limits, or you increase the wheel diameter, which reduces tractive effort. And traction, the ability to pull a load, depends on the weight on the driving wheels and the coefficient of friction between the wheel and the rail. On a steep grade, the weight shifts backward off the driving wheels, and traction drops. The Shay used a completely different approach. The cylinders were vertical, mounted outside the frame on the right side of the locomotive, usually 2 or 3 cylinders, depending on the size of the locomotive. The pistons drove a horizontal crankshaft, and the crankshaft drove a line shaft, a long steel shaft that ran along the right side of the locomotive, from the cylinders to the rear truck. The line shaft had bevel gears at intervals, and these bevel gears engaged with bevel gears mounted on each axle. Every axle, every wheel on the locomotive was driven. The gears provided a reduction ratio, typically about 1.5 to 1 or 2 to 1, meaning the wheels turned slower than the line shaft, but with much more torque. This gearing gave the Shay its characteristics. It was slow. Maximum speed for most Shays was 10 to 12 miles per hour on level track, and on steep grades, they operated at 4 to 6 miles per hour, walking speed. But the tractive effort, the pulling power, was immense. A Shay could exert tractive effort equal to 25 to 30% of its total weight, compared to about 20% for a standard locomotive. And because all the wheels were driven, all the locomotive's weight contributed to traction. There was no slipping, no loss of power. The flexible frame was equally important. A Shay was built on 2 or 3 trucks, 4-wheel assemblies that could pivot independently. This allowed the locomotive to conform to curves and to track irregularities. The line shaft was flexible enough to accommodate the movement between trucks. A 3-truck Shay could navigate curves that would derail a standard locomotive, and it could operate on track that was uneven, poorly aligned, or laid on a roadbed that shifted and settled. The combination of geared drive and flexible frame made the Shay ideal for logging railroads. It could climb steep grades, handle tight curves, and tolerate rough track. And it was rugged. The design was simple, robust, and maintainable in the field with basic tools. If a gear broke, you could replace it. If the line shaft bent, you could straighten it or fabricate a new one. The Shay was designed to be abused, and it was. Lima Locomotive Works became the primary manufacturer, though the design was licensed to other companies for specific markets. Production began in the early 1880s and continued through 1945, though the peak years were 1890 through 1920. During this period, Lima built approximately 2,700 Shays in various sizes and configurations. The smallest Shays, 2-truck models, weighed around 18 to 20 tons and were used for light industrial work and small logging operations. The largest, 3-truck models, built for heavy logging railroads in the Pacific Northwest, weighed up to 160 tons and were among the most powerful locomotives of their type. The standard configuration was the 3-truck Shay, which became the workhorse of the logging industry. A typical 3-truck Shay weighed 80 to 100 tons, had 3 vertical cylinders, 12 driving wheels, and could pull a train weighing 3 to 4 times its own weight up a 6 to 8% grade. The cost varied by size and era, but a large 3-truck Shay in the 1910s or 20s might cost $20,000 to $30,000, roughly $600,000 to $1 million today. For a logging company, this was a significant investment, but the return was immediate. A Shay could move in a day what would take weeks with animal power. Building a logging railroad for Shay operation was a different proposition than building a standard railroad. The track standards were minimal, the construction was cheap and fast, and the entire infrastructure was designed to be temporary. Logging railroads typically used narrow gauge track, 36 inches between the rails instead of the standard 56.5 inches. Narrow gauge allowed tighter curves and required less material for switches and cars. Some logging railroads used standard gauge, but narrow gauge was more common. The rails were light, 40 to 60 pounds per yard, compared to 90 to 130 pounds for mainline track. The ties were often rough-cut logs or slabs, not the dressed timbers used on standard railroads. And the roadbed was minimal. In many cases, the track was laid directly on cleared ground, with just enough grading to provide drainage. The route followed the terrain. If there was a slope, the track climbed it. If there was a ravine, a trestle was built. If the route needed to gain elevation quickly, switchbacks were used, zigzagging up the slope, with the train reversing direction at each level. The construction speed was impressive. A crew could lay a mile of track in a week, sometimes faster. The track was temporary, expected to last only as long as the timber in the area. Once the cutting was done, the track was pulled up, the rails and ties salvaged, and used elsewhere. The trestles, the wooden bridges that spanned creeks and ravines, were engineering marvels in their own right. Built entirely of timber, often from the same forests being logged, these trestles could be 100 feet high and several hundred feet long. They were designed to carry the weight of a shay and a loaded train, but they were not built to last. Many were temporary, expected to stand for a few years until the logging moved on. The construction was crude but effective. Heavy timbers for the framework, smaller timbers for the deck, all held together with spikes and bolts. No paint, no preservatives, just raw wood exposed to the elements. Some trestles were used for decades and became permanent structures. Others collapsed under the weight of snow or the rot of the timbers. The operation of a logging railroad was a daily routine of controlled chaos. A typical day began at the mill or the log landing, the central point where the railroad began. The shay would be fired up, the boiler brought to pressure, which took an hour or more depending on the size of the locomotive and how cold it was. The fireman, the crew member responsible for maintaining the fire and the steam pressure, would shovel wood or coal into the firebox, watching the gauges, building pressure to the operating range, typically 150 to 200 pounds per square inch. The engineer, the man who operated the locomotive, would check the mechanical components, the line shaft, the gears, the lubrication points. Once the locomotive was ready, the train would be assembled. Flat cars, simple platforms on wheels, would be coupled together and the train would head out to the cutting sites. The route could be 10, 20, 30 miles, climbing into the mountains, following the winding, steep track. The shay would pull the empty cars at a steady pace, maybe 8 to 10 miles per hour on the flatter sections, slowing to 4 or 5 on the steep grades. The sound was distinctive, a rhythmic chugging from the vertical cylinders, a clanking from the line shaft and gears, and the hiss and roar of the steam exhaust. At the cutting site, the cars would be loaded with logs. The logs were massive, old-growth timber, 40-foot lengths weighing several tons each. The logs were loaded using steam-powered loaders, or, in earlier operations, by hand with ramps and rollers. Each flat car could carry 3 to 5 logs, depending on the size, and a train might consist of 10 to 20 cars. The loaded train could weigh 500 to 1,000 tons, and the shay would pull it back down the mountain to the mill. The descent was more dangerous than the climb. Gravity was working with the train now, and controlling the speed required careful brake management. The shay had brakes on its driving wheels, but most of the braking came from the cars. Each car had a manual brake, a wheel that the brakeman would turn to apply friction to the wheels. The brakeman, usually 2 or 3 men, would ride on top of the loaded logs, moving from car to car, setting and releasing brakes as the engineer signaled with the whistle. It was dangerous work. The logs were slick, the train was moving, and a misstep meant a fall that could be fatal. Runaways were the nightmare scenario. If the brakes failed, or if the grade was too steep and the brakes couldn't hold, the train would accelerate, the engineer would lose control, and the train would race downhill until it derailed or reached the bottom. There are accounts of runaway logging trains traveling for miles, building speed, the engineer and fireman jumping off to save themselves, the train finally derailing at a curve or crashing into a structure at the bottom. The destruction was total. The locomotive wrecked, the cars destroyed, the logs scattered. Men died in runaways. Engineers who stayed with the locomotive trying to regain control. Brakemen who were thrown off when the train bucked and jolted. Workers on the track who didn't get clear in time. The companies tried to prevent runaways with procedures and equipment. Some logging railroads used dragging devices, logs chained to the rear of the train that dragged on the ground or on the rails, adding friction. Others used multiple shays on a train, one pulling, one or two at the rear pushing and providing additional braking. But the risk was inherent in the operation. Steep grades, heavy loads, primitive braking. It was a combination that occasionally resulted in disaster. Derailments were more common than runaways, but usually less catastrophic. The rough track, the tight curves, the heavy loads all contributed to derailments. A wheel would climb the rail, especially on a curve, and the car or the locomotive would leave the track. If it happened at low speed, it was an inconvenience. The train would stop, the crew would use jacks and levers and blocking to lift the derailed equipment back onto the rails, and the train would continue. If it happened at speed or on a trestle, it could be a disaster. Locomotives and cars tumbling off trestles, crashing into ravines, men killed or seriously injured. Boiler explosions, the catastrophic failure of the steam boiler, were a risk with any steam locomotive, and shays were no exception. The boiler operated at high pressure, and if the water level dropped too low, or if a seam or a rivet failed, the boiler could explode with devastating force. The fireman's job was to monitor the water level constantly, but in the rough operation of a logging railroad, with the locomotive pitching and rolling on uneven track, the gauges could give false readings. There are records of shay boiler explosions, though they were relatively rare. The explosions killed the crew, destroyed the locomotive, and often caused fires that spread to the loaded cars and the surrounding forest. The engineering of the shay was continually refined. Early models had 2 cylinders and 2 trucks. Later models added a 3rd cylinder and a 3rd truck, increasing power and traction. The line shaft was strengthened, the gears were improved, and the boilers were made more efficient. By the 1920s, the 3-truck shay was a mature design, reliable and powerful, the standard for heavy logging operations. But the shay wasn't the only geared locomotive. Competitors developed alternative designs. The Heisler locomotive, built by the Heisler Locomotive Works, used a V configuration of cylinders mounted under the boiler, driving a central shaft that powered the trucks through gears. The Heisler was smoother and quieter than the shay, but mechanically more complex. The Climax locomotive, built by the Climax Manufacturing Company, used 2 cylinders mounted at an angle, driving a central shaft. The Climax was used for lighter work and was popular in some regions, but the shay dominated the market. Of the approximately 4,500 geared locomotives built in the United States, about 2,700 were shays, roughly 60%. The shay's dominance came from its ruggedness, its simplicity, and Lima's manufacturing capacity and marketing. What could a shay do that a standard locomotive couldn't? The performance differences were dramatic. A standard freight locomotive of the same era, operating on mainline track, could pull a train of 1,000 tons or more on level ground, but would struggle on grades above 2%. A shay, on the same grade, could pull 3 to 4 times its own weight. A 100-ton shay could pull a 300 to 400-ton train up an 8% grade, and it could do this on rough track with tight curves. The steepest grades regularly climbed by shays were in the range of 9 to 11%. The Cass Scenic Railroad in West Virginia, originally built as a logging railroad, has sections with an 11% grade. Shays operated on this railroad for decades, pulling loaded log trains up the mountain. Today, the railroad operates as a tourist attraction, and the shays still climb the same grades, now pulling passenger cars instead of logs. The sight and sound of a shay climbing an 11% grade is visceral. The locomotive leans into the slope, the vertical cylinders chugging rhythmically, the line shaft spinning, the gears clanking, the exhaust roaring. The speed is walking pace, 4 or 5 miles per hour, but the power is undeniable. The train keeps moving, steadily, relentlessly, climbing a slope that seems impossible. The curve capability was equally impressive. Standard locomotives required curves with radii of several hundred feet to operate safely. Shays could handle curves with radii of 100 feet or less, 20 to 30 degree curves. The flexible trucks and the short wheelbase allowed the locomotive to conform to the curve, and the geared drive meant there was no loss of traction on the inside or outside wheels. Some logging railroads had curves so tight that the locomotive and the cars behind it bent visibly, the train snaking through the forest like a living thing. The operational reliability of the shay was a key factor in its success. Logging railroads operated in remote locations, far from repair facilities. The shay was designed to be maintainable in the field. The line shaft could be accessed and repaired without major disassembly. The gears were robust and could be replaced individually. The boiler and the cylinders were standard steam locomotive components, well understood by mechanics and engineers. A shay could operate for months with minimal maintenance, and when repairs were needed, they could often be done on-site with basic tools and materials. This ruggedness came at a cost. The shay was slower, noisier, and less fuel efficient than a standard locomotive. The geared drive consumed more coal or wood for the same amount of work because of the mechanical losses in the gears. But for logging operations, where speed wasn't critical and fuel was often cheap or free, scrap wood from the sawmill, the trade-offs were acceptable. The decline of the shay and the logging railroads that used them began in the 1920s and accelerated through the 30s and 40s. The primary cause was the development of trucks and roads. Gasoline and diesel trucks, with their flexibility and lower infrastructure costs, began to replace railroads for log transport. A truck could go wherever a road could be built, and roads were cheaper and faster to build than railroads, even temporary logging railroads. By the 1930s, trucks were hauling logs in operations that would have required railroads a decade earlier. The economic depression of the 30s reduced logging activity, and many logging railroads were abandoned, the track pulled up and sold for scrap. World War II brought a temporary resurgence as demand for timber spiked, but after the war, the shift to trucks was irreversible. Diesel locomotives, introduced in the 1940s, offered more power and efficiency than steam, but for logging, the diesel's advantages were less significant than the truck's flexibility. By the 1950s and 60s, most logging railroads were gone. The last commercial operations using shays continued into the 70s in isolated cases, but by then they were anachronisms. The track was pulled up, the trestles collapsed or were dismantled, and the locomotives were scrapped or abandoned. Some were left in the woods where they had worked, slowly rusting, reclaimed by the forest. But not all were lost. Preservationists, rail fans, and historians recognized the significance of the shay, and efforts were made to save examples. Museums acquired locomotives, and heritage railroads, tourist operations running on historic routes, restored shays to operation. Today, approximately 160 shays survive out of the 2,700 built. Of those, perhaps 15 to 20 are operational, maintained by heritage railroads and museums. The Cass Scenic Railroad in West Virginia operates several shays, pulling tourist trains up the same steep grades they climbed with logs decades ago. Roaring Camp Railroads in California, the Mount Rainier Scenic Railroad in Washington, and others offer rides behind shays, preserving the experience of geared locomotive operation. Standing next to a shay, even one that's cold and static in a museum, you get a sense of the engineering and the purpose. The vertical cylinders, the exposed line shaft with its spinning gears, the massive frame and the small wheels. It all looks strange compared to a standard locomotive. But the strangeness is functional. Every element of the design serves the purpose. Climb steep grades, handle rough track, pull heavy loads. When a shay is under steam, the engineering comes alive. The cylinders chuff rhythmically. The line shaft spins. The gears mesh and turn, and the entire machine vibrates with purposeful power. It's loud, mechanical, visceral. There's no hiding the machinery, no streamlining. It's all exposed, all visible, all working. Ephraim Shea didn't get rich from his invention. He made enough from the royalties to live comfortably, but he spent most of his later years in logging and related businesses, not in engineering or manufacturing. He died in 1916, known in the logging industry, but not celebrated widely. His obituary in the local paper was brief, noting his death and his contributions to the industry, but there was no national recognition, no sense that he had changed an industry. But the locomotives that bore his name did change the industry. They opened forests that had been inaccessible, enabled logging operations in terrain that would have been impossible with animal power or standard railroads, and moved billions of board feet of timber that built cities and infrastructure. The Shea locomotive was a specialized tool designed for a specific purpose, and it excelled at that purpose. It wasn't fast, wasn't efficient in the conventional sense, but it could climb mountains, and that was what mattered. The logging railroads are mostly gone now. The track pulled up, the roadbeds overgrown, the trestles collapsed. But the routes are still visible if you know where to look. Old railroad grades, cut into hillsides, winding through the forests. The scars of trestles, abutments, and pilings still standing. And occasionally, rusted rails, spikes, and ties, remnants of an industry that transformed the landscape. The Shays that survive are monuments to an era of engineering pragmatism, of solving problems with ingenuity and mechanical elegance. They're also reminders that technology is temporary, that even the most successful designs are eventually replaced by something cheaper, faster, more flexible. The Shay climbed mountains for 60 years, and then it was made obsolete by a truck on a dirt road. But for those 60 years, it was irreplaceable. And the forests remember.